How can there be a heat source or heat generation? Heat generation or heat source systems could be due to nuclear reaction or electrical current passage or exothermic chemical reaction. Now I shall consider a plain wall with the heat generation or heat source. Now I shall consider a wall the length is L and L. The central axis is x is equal to 0. Here x is equal to plus L and here x is minus L. There is throughout heat generation. Let Q dot is equal to heat generated per unit volume in watts per meter cube. Please note that there is uniform heat generation. Here the assumptions in the analysis are: number 1, steady state heat transfer; number 2, uniform heat generation; number 3, constant thermal conductivity; number 4, one-dimensional heat conduction. So if you bring in the steady state, if you bring in the generalized heat conductivity equation, that is dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square plus Q dot by K is equal to 1 by alpha into dou T by dou tau. In this case, dou square T by dou y square is 0, dou square T by dou z square is 0, dou T by dou tau is 0. Why? Because it is one dimensional and also it is steady state conduction heat transfer. Dou T by dou tau should become 0. So the resulting equation will be d square T by dx square plus Q dot by K is 0. We have to solve this differential equation with the help of boundary conditions. Now, if you separate the things and integrating, we get dt by dx is equal to minus Q dot by K into x plus C1. Again integrating, we get T is equal to minus Q dot by K into x square by 2 plus C1x plus C2. C1 and C2 are constants of integration that are to be obtained or calculated from the boundary conditions. For the boundary conditions, we specify the temperatures on either side of the wall. That is, the temperature on either side of wall, that is T is equal to TW at x is equal to plus or minus L. Because the temperature must be the same on each side of wall C1 should be equal to 0. The temperature at the midplane, that is x is equal to 0, is denoted by T0. Therefore, temperature distribution would now become T0, T minus T0 is equal to minus Q dot by K 2K into x square. That is non-dimensional form. We can write as x by L whole square, a parabolic distribution inside the plane wall. The midplane temperature T0 could be obtained through an energy balance. That is, at steady state condition, the total heat generated in the wall must be equal to heat loss at sides or at faces that is 2 into minus Ka dt by dx at x is equal to L. That should be equal to the total heat generated in the slab, where Q dot is the heat generated per unit volume and 2L is the total width of the slab. A into 2L is the total volume of the slab. Whereas dt by dx at x is equal to L could be obtained as by differentiating the above equation into 2x by L square at x is equal to L, that is Tw minus T0 into 2 by L. Thus, minus K into Tw minus T0 into 2 by L is equal to Q dot into L. Therefore, T0 is equal to Q dot into L square by 2K plus Tw. Therefore, temperature distribution now is T minus Tw by T0 minus Tw is equal to 1 minus x square by L square. Where T0 is the midplane temperature. T wall is the wall temperature at x is equal to plus L or minus L. T is the temperature at any x measured from the midplane. L is the half of the total width of the slab. Now I shall consider a case of cylinder with heat sources. Consider a cylinder of radius or with uniformly distributed heat sources and constant thermal conductivity. K. If the cylinder is sufficiently long, temperature may be assumed to vary only with the radius. If the length of the cylinder is very long, then the differential equation would become d square t by dr square plus 1 by r into dt by dr plus q dot by k is 0. Here the assumption is one-dimensional heat transfer, steady state heat transfer, constant thermal conductivity. The boundary conditions are T is equal to TW at small r is equal to capital R, that is wall temperature, and heat generated equals heat lost at surface, that is total heat generated is Q dot into pi r square L, that is equal to minus K 2 pi RL Ka dt from Fourier law, dt by dr at r is equal to r. Left hand side is heat generated, right hand side is the heat conducted at the surface. Since the temperature function must be continuous, at the center of the cylinder, we can write dt by dr is equal to 0 at r is equal to 0. That is, temperature is maximum at the axis. So rewriting the differential equation, r into d square t by dr square plus dt by dr is minus q dot r by k, and note that r into d square t by dr square plus dt by dr is equal to d by dr of r into dt by dr. Integration yields r into dt by dr is equal to minus q dot r square by 2k plus c1, and again integration yields t is equal to c1 log r plus c2. c1 and c2 are constants of integration that are to be obtained from the boundary conditions. From second boundary condition, above, dt by dr at r is equal to capital R is minus q dot r by 2k, that is equal to minus q dot r by 2k plus c1 by r, implies c1 is equal to 0. It is also obvious that from this, at r is equal to 0, the logarithmic function becomes infinite. C1 must be 0. Therefore, from the first boundary condition, T is equal to TW is equal to minus Q dot R square by 4K plus C2 at R is equal to R. So that C2 is equal to TW plus Q dot R square by 4K. So the final solution for temperature distribution is T minus TW is equal to Q dot by 4K into R square minus R square. Or in the dimensionless form, T minus TW divided by T naught minus TW is equal to 1 minus R by R whole square, where T naught is centerline temperature, that is at R is equal to 0, which is given by T naught is equal to Q dot R square by 4K plus TW. This is the maximum temperature, we can say. So if you see the temperature distribution along the axis, along the cross section of the pipe is, this is T naught, maximum temperature. TW is the wall temperature on surface temperature. T naught is the surface temperature. T naught is the centerline temperature or axis temperature. Now let us solve a problem regarding the heat generation. The problem is given like this. A current of 200 amps is passed through a stainless steel wire conductivity K is equal to 19 watts per meter degree centigrade, 3 mm in diameter. The resistivity of steel wire may be taken as 70 micro ohm centimeter, and the length of wire is 1 meter. The wire is submerged in a liquid at 110 degrees centigrade and experiences a heat transfer coefficient of 4 kilowatts per meter square. Calculate centerline temperature of wire. The solution to this problem can be given like this. All the power generated in the wire due to passage of current must be dissipated by convection to liquid. That is, power is equal to I square R, where R is the resistance, which is equal to heat generated. That must be equal to the HA into TW minus T infinity. Let us calculate electric resistance of wire first of all. That is rho L by A, where rho is the resistivity. 70 into 10 power minus 6, length is 100 centimeters, divided by pi r square, that is 0.15 whole square. This becomes 0.099 ohms. That is the electric resistance. Please note that here this is the cross-sectional area in the denominator. In the here it is the surface area. This is surface area, whereas this is cross-sectional area. Surface area of wire is equal to pi dl. So from this above equation 1, energy balance equation for steady state, we get 200 whole square into 0.099 is equal to 4 kilowatts, that is 4000 watts per meter square Kelvin. A is pi dl, pi into 3 into 10 power minus 3 into L is 1 meter into TW minus 110, that is equal to 3960 watts. Therefore, T wall is 215 degrees centigrade. Heat generated per unit volume Q dot is calculated from power is equal to Q dot into volume, that is Q dot into pi r square L, where r is the radius, implies Q dot is equal to 3960 power divided by pi into 1.5 into 10 power minus 3 whole square into 1 is becomes 560.2 megawatt per meter cube. Therefore, centerline temperature of wire could be calculated as T naught is equal to Q dot into R naught square by 4K plus TW. This is equal to 5.602 into 10 power 8 I'm sorry, 10 power 6, 10 power 8, because 560.2 megawatts into 10 power 8 into 1.5 into 10 power minus 3, that is the radius of the wire, divided by 4 into 19 plus 250. So this result is 231.6 degrees Celsius. That is the centerline temperature of the wire. Hence the problem. Now I shall do a problem regarding the heat generation inside the cylindrical wire under steady state conditions. What is the temperature distribution? Let's calculate. The problem goes like this. The problem is given as an electrical transmission line made of a 25 mm annealed copper wire carries 200 amps and has a resistance of 0.4 into 10 power minus 4 ohms per centimeter length. If the surface temperature is 200 degrees centigrade and the ambient air temperature is 10 degrees centigrade, determine the heat transfer coefficient between the wire surface and the ambient air and the maximum temperature in the wire. Assume K is equal to 150 watts per meter Kelvin. The solution to this problem could be given as the heat generated in the conductor is equal to the rate of heat generated in the conductor Q is equal to I square R, where I is the current and R is the resistance, 200 whole square into 0.4 into 10 power minus 4, that is 1.6 watts per centimeter length, that is 160 watt per meter length. This much heat is generated. Therefore, heat generated per unit volume Q dot is equal to Q divided by V, that is 160 divided by pi 0.0125 pi r square into 1 meter length, that is 325.95 watts per meter cube. The maximum temperature in the wire occurs at the center. Obviously, because the distribution is parabolic, it is like this. The maximum temperature in the wire would occur at the center. This is the T max at the center line temperature. The center line temperature is given by TW, that is wall temperature, plus Q dot by 4K into R naught square, where R naught is the radius of the wire, that is surface temperature 200 plus 3.2595. Please note that 325.95 is kilowatt. I'm sorry, it is the kilowatt per meter cube. 3.2595 into 10 power 5, that is so many watts per meter cube, into 12.5 into 10 power minus 3, this is a radius in meters whole square, divided by K is 4 into 150. K is 150 watts per meter Kelvin. So the resultant is 200.08 degrees centigrade. This is the center line temperature. Also, the surface temperature and the fluid temperature are related from TW is equal to fluid temperature plus R naught Q dot divided by 2H. This is from energy balance equation. This equation is obtained from the energy balance equation, that is the heat generated in the wire should have to be given to the surrounding fluid by convection for steady state conditions. So from the energy balance equation, that is heat generated in the wire is equal to heat lost at the surface by convection to the fluid. So from this energy balance equation, this equation is obtained. Therefore, from which H could be calculated as R naught Q dot divided by 2 into T naught minus TW, that is 12.5 into 10 power minus 3, that is the radius. Q dot is 3.2595 into 10 power 5 divided by 2 into 200 is the wall temperature minus fluid temperature. The H value will be 10.72 watts per meter square Kelvin. By seeing the H value, we can say that it is free convection from the surface of the wire to the surrounding fluid, that is air. Hence the problem. Now I shall do another problem given on fins. One end of a very long aluminum rod is connected to a wall at 140 degrees centigrade, while the other end protrudes into a room whose air temperature is 15 degrees centigrade. The rod is 3 mm in diameter and the heat transfer coefficient between the rod surface and environment is 300 per watts per meter square Kelvin. Estimate the total heat dissipated by the rod taking its thermal conductivity as 150 watts per meter Kelvin. The solution to this problem could be given like this. This is the wall. A rod is protruding like this. This is the base temperature T0. H is the convection heat transfer coefficient from the fin to the surrounding fluid, and T infinity is the fluid temperature. D is the diameter of the rod, and L is the length of the fin. It is a pin fin. Please note that it is a pin fin. Since the rod is very long, the rate of heat transfer Q is equal to square root of HPKA into T0 minus T infinity. Here K is 150 watts per meter Kelvin. Perimeter is pi d, that is 9.424 into 10 power minus 3 meter. And A is the cross sectional area. This is the profile area. This is A is pi by 4 d square into 10 power minus 6 meter square. Base temperature is 140 Celsius. Fluid temperature is 15 degrees Celsius. The rate of heat transfer is 300 into 9.424 into 10 power minus 3, that is perimeter, into 150. Area is 7.068 into 10 power minus 6 into T naught. Base temperature is 140, fluid temperature is 15. The resulting answer is 0.0547 into 125, that is 6.843 watts. This is the rate of heat transfer, assuming that the rod is infinitely long. That is a case 1. Case 1 in the fins analysis. Case 1 is infinitely long. Case 2 is fin tip insulated. Case 3 is fin is finite in length and loses heat by convection from its tip. That is case 3. Hence the problem.